So push-down automata is a special automata which takes use of stack for the purpose of recognizing the languages. The languages which are generated by context-free grammar, CFG, those languages are referred as CFLs. Okay, those languages are referred as CFL, and this CFL category of language is accepted or recognized by PDA, push-down automata. Push-down automata work in the fashion of LIFO, that everybody knows, right? That is last in, first out, which means the symbol which is push into the stack last will get popped first. Okay. So at any moment of time, when we talk in terms of the working of push-down automata, on the scanning of each input symbol, PDA, what it does, basically, it doesn't scan only input symbol, rather it checks for input symbol and stack top, these two symbols. Based on what is the current state, what is the input symbol, and what is available on the stack top, PDA performs operations such as first is change of state. Okay. Second is change of stack. Stack position changes. Either it pops a symbol from the stack or it push a symbol onto the stack. So basically, when we try to represent a transition for working of push-down automata, it can be written like this: del of Qi on the input of Xi when the stack top is Si. What it does, it changes the state, say from Qi to Qj, and it performs some operation on stack. That means Si is replaced with Srj here, right? Where I we are referring as a current case and J we are referring as a next state. Okay. So what is required here is what is the current input, what is the current stack top, and what is the current state. Based on that, it decides what would be the next state and what would be the replacement symbol on the stack, whether this stack top should be removed or some other symbol can be pushed onto the stack. I will take one example how it can be visualized. Let's say we have state as a Q0 where input is 0, and on the stack top, let's say we have a symbol Y. Okay, let's say we have a symbol Y. So we can write it like this. Next state, let's say Q1, and say X is the another symbol which will be pushed onto Y. So it can be represented as X pushed on Y. This is the one way of representing the transition function for push down automata. The other way is we know that either something can be pushed onto the stack or we can pop the top of the stack symbol. So which can be, let's say, pop situation. If we want to write, we can write the same scenario like this: Y, and this, let's say this Y is going to be popped. So Qj, comma, Y is popped. So that means on the stack top, whatever was the earlier symbol, that symbol has been taken out. So we have epsilon in the place of that Y. So this Y has been removed. So we have epsilon in its place. So ultimately what will happen? If one symbol get popped from the stack, the next symbol whichever is available, that will become the stack top. So up, down below this Y, if let's say we have another symbol Z, this Y is replaced with epsilon. So ultimately epsilon means nothing, a string with 0 length. So this Z will become the new stack top. Is this clear about this? the way of representing the operations such as push and pop in case of push down automata? Is this clear to you all?
Yes, sir.
Okay, great. So let's go for the tuple definition for push down automata. Now we know that push down automata requires allowable set of stack symbols, the stack symbols which can be pushed onto stack. It also requires the set of symbols which can be considered as the input symbol. Okay. Similarly, finite set of states, as in the case of finite automata, finite set of input symbols we already talked about. And apart from that, we need a special symbol which is referred as a Z0, which we call as a bottom of stack. Right? If you don't have anything on the stack, it means on the stack top you have Z0. So a tuple definition for PDA can be given as Q summation tau delta Q0 Z0 and F, where capital Q is nothing but the finite set of states. Summation or alphabet is referred as a finite set of input symbols. This tau is referred as a finite set of allowable stack symbols, the symbols which we can push onto the stack. Delta is nothing but the transition function. Q0 represents the initial state. Z0 represents special stack symbol, which is referred as a bottom of stack indicator. And capital F is nothing but the finite set of final states. We have recently seen in the previous slide, we have seen that the way to write delta for PDA is like this: 0 xi si use qj comma rj, right? So we can very well say that the transition diagram or transition function for push down automata has a mapping of q cross summation cross tau leading to q cross tau star. Now, what is the meaning of this? That from any state from q on the input symbol from the summation alphabet, and when some si from tau is available, it will lead it to another state from q, and here we have represented tau star because we have seen that this could be either epsilon in case of popping of the symbol, or it could be more than one symbol, like we have seen x was pushed onto y, so more than one symbol exists, so we are taking tau star. This x or y, these both will belonging to tau, that is set of allowable stack symbols. So this is basically the way to write transition mapping for push down automata. Is this clear? Is this clear to you all?
Yes, sir. It's,
Okay.
Yes, sir, it's clear.
can you
Let's
show
go.
an example?
Yeah, we'll go for examples now. I have given two examples. I have written two examples here on the left hand side. Design push down automata to accept the following languages. First language is L equals to 0 raised to power n, 1 raised to power twice n, where n greater than equal to 0. Now, what does it means? That we have set of zeros, sequence of zeros followed by sequence of ones, such that if we have n number of zeros, the number of ones would be twice to that of it. That means if we have n equals to 1, we'll have two number of ones. So if we take like say n equals to q, our string would become w would become what? 2 times 0 followed by 4 times 1. Is this clear? And the condition mentions that n greater than 0. That means value of n would be 1, 2, dot, dot, dot. Can have any value. So minimum length for W would be what? If we take n equals to 1, n equals to 1, your W's length would be 1 0 plus 2 ones, that is 3. Is this clear? So let's assume that we are representing a set of strings which belongs to the given language. Okay, and that set we are representing by W. So smallest length string would be 0 1 1. Next would be 00 4 ones, 000, then we will have 6 ones, and so on. Right? So let's assume that for each 0, what we will do is we'll push X onto the stack. Basically, what we need to see is that do we have twice number of ones as that of number of 0, and at the same time, do we have the sequence followed, that is zeros followed by ones. So what we will do, let's take this. If we are taking case, we'll push for this 0, we'll push X onto stack. As soon as we get 1, for each eventh one, we'll pop one symbol from the stack. So basically, first one we will skip. For the second one, we'll pop the symbol from the stack. Okay, this process will continue. Excuse me, till we get all ones over. Once the number of ones is over, we need to check, have we reached to the bottom of stack? If we are reached to the bottom of stack, it means we have twice number of ones as that of zeros. Same thing can be explained in terms of this string in a way that,
Sir, can you please explain that portion once, what
yeah,
you have explained now? Because
I'm explaining it for this new string. Like what we have here n is equals to 3. So ultimately 3 number of zeros followed by 6 number of ones. So what we will do, for each 0, we need to check, do we have twice number of ones than that of zeros? So for each 0, we'll push one symbol onto stack. Okay, let's say we are pushing X for each of such a zeros which are coming in the input. So for first 0, we have pushed one X. For second 0, we'll push another X. For third 0, we'll push again third X. Okay, as soon as we get 1, for each odd one, we will do nothing. For each eventh one, we will pop one symbol from the stack. So this is odd one, so leave it. This is eventh one, pop the symbol from stack. Again, odd one, leave it as it is. For eventh one, pop this symbol. Ultimately, when all ones are over, at that time, we have all X also removed. For each 2 ones, one X was removed. And when we are getting epsilon here, that means end of the string. At that time, we will have Z0 on the stack. Is this clear? So this logic will continue. So how to go for it? How to build the push down automata? We'll have transition diagram drawn for this. Okay, for this case. What we have mentioned is that at the beginning of the process, our stack contains Z0. And we are saying Q0 as our initial state. Okay, Q0 is the initial state. So at the beginning, we will have Z0. And since the value of n is greater than 1, our minimum length string is this. That means first symbol, let it be any case. If it is a valid string, our first symbol is 0. Okay. So what we will do is 0, comma Z0. That means in Q0, when the input was Z0 and on the stack top we have Z, input was 0 and on the stack top we have Z0. We will push X for this each 0 onto stack. So this is the first case that for the first 0, when the stack top was Z0, we pushed X onto Z0 like this. For the remaining zeros in the string, apart from first one, what we will do, 0 as a symbol, but on the stack top we no more have Z0, rather new stack top is X. We'll say 0 comma X. If we are getting such a situation, that means the 0 which we have received is not the first 0 in the sequence. We will push another X on this X, that is this. So on stack top, we will have new X available. This new X will be available on the stack top, which is pushed on the top of this old X. Okay, is this clear about pushing X for each 0?
Yes, sir.
Now this process will continue, process of pushing X onto Z0 till we don't get 1, right? So on the receipt of 1, what we need to do is first one to be skipped. For each second one, we'll pop one symbol from the stack. So let's represent. If we get 1, at that time, it is but natural we will have X as a stack top. X. For first one, leave X as it is. Okay. Q1. For the second one, whichever we get 1 on X, pop that X from the stack. So basically what we did, as soon as we received the second one, this was our first one. So we kept stack top as it is. For each second one, we are popping this X from the stack. New state. And this process will repeat. What process? Skipping 1, 1. That means keeping the stack top as it is and doing nothing for the first one. And for each second one, pop 1X from the stack. This process will continue, right? And this process will be continued till all the ones are over. And the condition is that one should be available twice time than that of zeros. So ultimately, this epsilon, whenever we'll get it in Q2 only. So if in Q2 we get epsilon, in that case only we need to proceed further. Now proceed further means what? It is but natural that if we are getting epsilon, that is the end of the string, and the string is as per our description, all X would have been popped like this from the stack. Okay, so stack top should be Z0. If the string is valid, when your ones are over, that means you are getting epsilon in the string. Stack top should be Z0. If it is the case, only in that case you must move to Z0. You must move to final case. What is final state? We are referring QF as a final state here. Is this clear?
Yes, sir, it's clear.
So we'll try to see whether it really works. This diagram really works for the cases which you have seen or not. Let's refer the case number 2. This case will go for. Okay. Refer, let's say this as a rule number 1, this as a rule number 2, this as a rule number 3, rule number 4, rule number 5, and rule number 6. Okay. At the beginning, what we will do is we'll start with Q0. Del of Q0. Our input is 00 and 4 ones, comma, on the stack top we have Z0. We are talking about drawing proliferation diagram for the string, right? First section indicates state, current state. Second section indicates the input available on the tape. Third section indicates the stack position. Initially, stack we have Z0. In input we have 00 followed by 4 ones. And then in the state configuration, current state is Q0. So let's go for check which amongst these all rules matches with the current scenario. Current scenario says that state is Q0, current input is 0, and stack top is Z0. If we see here, Q0 is this state which has three rules available. Rule number 1, rule number 2, and rule number 3. Amongst these three rules, first rule matches with the current scenario. That is state Q0, input 0, and stack top as a Z0. So on the application of rule number 1, we have what? Since it's a clean closure, state is kept as it is 0. This first 0 got consumed. So input we have left with single 0 followed by 4 ones. And on stack, for this first 0, according to rule number 1, we have pushed X on the stack. So X on the top of Z0. So this is your after application of rule number 1. Now the current scene is Q0, input is 0, and stack top is X, which is reflected by or which matches with rule number 2. Result is what? Q0 to be kept as it is. On the top of this earlier X, we are pushing in another X. So let's say Q0, this 0 got consumed. So 1, 1, 1, 1. We are left with 4 ones only. And on the top of this X, and another X has been pushed. So this is your state representation. Next, Q0, 1X, which is reflected by or matching with the case number 2, rule number 3. So what would be the resultant out of this? Arpita, can you tell me what is the resultant out of it? Q0,
Sir,
when the
in the place of 1 means when we'll consider 1, so for the first odd one will be remaining as it is. And when we'll go for the next rule, the when there is even 1, so
correct. So
the
what we are
first
doing
X
is
will be removed.
X will kept as it is, right? Rule number 3 says X should be kept as it is. That is stack top will remain unchanged,
Yes,
and this 1 will get consumed, right? And the state change
yes,
would be
sir.
there. State would be changing from Q0 to Q1. So Q1, first one got consumed. We have left with 3 ones, followed by stack remains unchanged. Okay. Now Q1 1x, Q1 1x, rule number 4 matches with that. Rule number 4. The result would be what? Q1
So there will
1x.
be 1X will be removed and epsilon will be added.
Correct. X will be removed and epsilon will be added. That means epsilon means string with 0 length, right? So X will be removed
Yes,
from the
sir.
stack. So we will be left with tail of, instead of Q1, now state changed to Q2, correct? And we are left with 2 ones only, and this X will get removed. So we will have just one X available on the stack. Next, Q2 1X, Q2 1X, keep the X as it is. Ultimately, we'll go to Q1 again. First one will get consumed. X will remain as it is. Z0 will remain as it is. Next, Q1 1X, which matches with the rule number 4. Okay. So we have Q2, right? This one will get consumed. So we have left with epsilon here. And similarly, for this rule number 4, we are removing this X from the stack. So this X will get removed. So on stack top, we will have Z0. Q2 epsilon Z0 matches with the rule number 6. So rule number 6 gets matched here. Okay. So what we have is QF as a final state, epsilon, because after epsilon we don't have anything, all inputs from the input string has been consumed already. Stack top is Z0, right? So epsilon QF epsilon Z0, no state is shown here on QF. That means we are halting here, and it is nothing but, since this is a final state, we will say that the given input was as per the description. So input got accepted. Is this clear? So this is the
Yes,
way in
sir.
which push run automata can be constructed. Okay. Now this is just a construction of push down automata. We'll go for writing tuple definition also for this particular case. Now, how many state do we have used here? Those all state will become part of capital Q. So we have 1, 2, 3, 4, 4 states, which are nothing but Q0, Q1, Q2, and Qf. So this is our finite set of states for PDA, constructed PDA. Summation is basically what? Finite set of input symbols. Let's look for the case or the symbols which are represented here on the transition as a first symbol. We have 0, 0, 1, 1, 1. That's all. Epsilon, no need to represent. Basically, we have two symbols available, 0 and 1. This is nothing but our finite set of finite set of input symbols. Let's go for tau. Tau is nothing but this set of symbol which is available. This followed by this followed by this. So let's check which different symbols do we have. We have X, right? Here also X is available. Z0, Z0. Here also X, 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 Z0, Z0. So this is our finite set of allowable stack symbols. Delta is what? Delta is a transition function which is already shown in the diagram here, and its mapping is, we have already seen in the last slide mapping. What? Q cross summation cross tau leads to Q cross tau star. This is our delta. Q summation tau delta. Our initial state is Q0, right? Initial state. This is our Q0. Then Z0 is available. That is bottom of stack indicator or special stack symbol, it is also referred as. And capital F is nothing but the finite set of final states. So how many final states do we have here? Just one, right? Which is nothing but QF. So this is finite set of final states. So this is the way in which we write tuple definition for the constructed PDA. Let's say M is equals to Q summation tau delta Q0 Z0 F. This is our PDA for the first language, that is L equals to 0 n 1 to n. Any queries about this example?